Once again, good evening, everyone, and welcome to this NXP Campus Connect program. This is our flagship program, which is running almost 3 years now. And just for your information, on every first Tuesday every month, we are running VLSI track, and third Tuesday every month we are running a system engineering topics, which is involved in software, how software hardware is integrated, validation activities, and all those things related to that. Today, as you know, today is the first Tuesday of September month. So today is a VLSI topic, which is Parul is visible, who is our expert from analog IP team, and he is going to share more details on analog IPs and all, the complete overview of the system. And thank you, Sivnadar University Chennai branch for giving us an opportunity to share details on analog IPs and all, which will be very helpful for students. And our country head, Mr. Hitesh Garg, is a very dynamic leader. He's always very supportive on all these programs. So NXP India management team is committed for supporting universities, students, faculty members, and we are running several such programs. Like one of this is the Campus Connect program. Then we are running AIM, which is artificial intelligence and mobility programs, which is mostly for students to learn the integrated environment, how the software and hardware is going to be integrated, and the new technologies are going to be implemented on that platform. Then there are other events like hackathons we are doing on a regular basis, and then we are running labs, and parallelly we are hiring a lot of talents from Indian universities. NXP India is basically operating from 4 locations in India. The Noida is more of software and hardware design centers, and then in Bangalore similarly more software part, security, UWB, a lot of things we are doing from Bangalore branch, and then the connectivity stuff in Pune, a lot of Ethernet, Bluetooth, Wi-Fi, and all those things, and then the 5G related software infrastructure development we are doing it in Hyderabad. So from these 4 locations we are operating. So without much investing time on these all things, once again thank you Sivnadar University for giving us an opportunity, and thank you for all your time. Now I welcome Parul, who is having 25 plus years of industry experience in this one. He is our expert from the analog domain. Analog is a very critical and the niche skill set, which is a very complex things. So Parul will make our life easy to understand all those things. I'm very hopeful. Let's welcome Parul to this NXP Campus Connect platform. And we have this session is hosted by Sivnadar University Chennai branch, and a lot of other guys online, plus our NCGs are also part of this. So over to you, Parul.
Thank you, Manishji, for your intro, and I would thank everyone from Sivnadar University Chennai branch, and I can see the lot of crowd in the auditorium. That's very heartening to see a lot of attendance here. We already have 100 plus people online already. So I'm hoping that everyone will have a good time here. Okay. So let me just start about the presentation. Let me just share and just go to the basic stuff. Okay. So let me just share my screen and see where we come up. Is my screen visible?
Yes. Make it full screen here.
Yeah, just so.
Yes, perfect. Go ahead.
So is it full now?
Yeah.
Okay. So the talk that I'm going to give is on analog design deep dive in SoCs. So analog we know is a basic form of design where we use electronic circuits, very common in electronics and electrical circuits. And SoCs are system on chips integrated systems where we put not just analog but other stuff. So I'll start here one by one slowly. So in terms of, first of all, agenda is like importance of analog design. What is the importance of analog design? Then we will look at some of the analog and digital subdivision in the modern SoC, which is our basic chip. Analog and digital system characteristics and differences. Some amount of body of knowledge is required to be analog designer, so that you can have some kind of pointers to where you can study things. Typical analog blocks used in modern SoC is the kind of blocks we do or are available in the contemporary designs. Some of the things will go towards the future trends in analog and digital design and analog design as well. Then some of the examples from the NXP on analog and mixed signal products, and then in the end Q&A. Okay, so let me just go to my next slide. So if we look at the real world, it is analog in nature. If you can look at the people around, someone is driving, then there is a, let's say, windmill, or someone is in an operation theater or somewhere. So the real signals come like sound, picture, motion, touch, even temperature. All these things are analog in nature, which means what is analog, we will come nature, but primary, let us say, it is analog. And digital signals, basically they come after, from once we get the analog from the physical world, then we go to the digital world later on. Okay, let me just come to that. So the way it is this: there is a some kind of input sensor. This could be your camera or microphone or whatever. There is some level of signal processing around that, and then there is analog to digital conversion, ADC module. And with this conversion you can actually get your data in the digital format. Now here comes the crux of the digital systems that we talk about: signal processing. Whatever digital signal is there from analog domain, it is converted into digital domains. It is processed. If we need to take action and give it back to the real world, then we typically do it through some kind of data DAC, where we actually convert digital into analog to be able to communicate with the real world, and to the output actuator. So actuator could be anything like your motor, or it could be something like your, let us say, brake in the car or whatever, right? Where we want to basically have the impact. Okay. In order to work like this, electronic chips, they require power supply, and some of the external stuff like clock signals are required. Some reference voltages and currents are required, and sometimes high speed interfaces are required. So each of these perform a different kind of function. Like your high speed interfaces are for connectivity. What Manish was talking about, we need to be able to connect our data of our chip to some other data. It could be your PC, or it could be your host processor, it could be your cloud or somewhere there. Okay. On the input side, maybe we have looked at receivers, microphones, touch screens, motion sensors, temperature, gyroscope, optical sensors. All these things are analog basically on the sensor side. On the output side, it could be your transmitter, speaker, display, or it could be your LED bulb also, or LED. Okay. So this the system that we looked here, it is typically manifested as a part of a system on a chip, which is SoC. SoC is a block which is having many of these things put together, and these things, along with the surrounding things, they become a part of a PCB chip, system on board. Okay, the goal of the design is to basically have most of the things inside this chip only. As much as functions we can bring in, we bring in, and very few functions which are required, they are actually talking to external world. If you look at carefully, the connectors are much bigger than the chips themselves. These are all connectors you must have seen in the lab. This one, this one, this one. In the periphery you have got connectors, in the center you have got chips, and some capacitors around that. That is typically how a board would look like. So in terms of like, when we do SoC development system on chips, so there's an ecosystem around that. So in terms of solution stacks, there are clouds. So clouds are centralized places where you have got hundreds and thousands of machines who would do all the compute part. And there you can have like synthesized intelligence, and where you can run AI and ML stuff for analytics and actions. Then software stack is another thing. These are the kind of things that run on your board or PCB, and they would be actually having multiple layers of software, right from controlling the hardware at the lowest level to some data transfers, understanding the protocol and communication, and then talking to operating systems and all that. So they came in this kind of sequence, like firmware, bootloader, device drivers, application software. So each of these are very layered layered, and specialists work in each of these actually areas. In terms of hardware solution, there would be like PCB boards having peripherals, validation is there, testing and system design are there. So they have slightly nuances in each of these. Validation is where you check your hardware at a basic level, at the function level. Then there will maybe augmented testing where you go to the using like operating systems, and then some level of system design and interoperability between the systems. So all the gadgets that you use, they go through all these rigorous layers of testing. In fact, testing is a very big part of design activity itself. Then coming to design, the chip design. So there's a digital design, which is typically done in form of coding, RTL coding, verification, system C, and MATLAB modeling. Below digital design, we have put circuit engineering, which is the work that I do, and this is which is the major crux of this presentation, circuit engineering. So here we talk about like circuit design, verification, layouts, and then MATLAB modeling is there. It comes in both ways if you want to just model a system at a higher level of thinking, just like your control system boxes. Okay. Device engineering comes below circuit engineering, where they target to make device with known characteristics, RLC or threshold voltages and all that. So that area is basically trying to infer usable devices out of a process steps. Below device engineering is process engineering. It is here basically you use like physics based processes to realize usable design devices like your CMP, ion implantation, and doping, diffusion, all that device engineering, process engineering. So you try to use wafer for something which will convert it into a device, and those set of steps are called process. Okay. Underneath this is a like equipment manufacturers, the people who would make all this equipment work, the process equipment. So equipment manufacturer would make physics based devices, then process engineers would make a recipe out of it to make inductors, capacitors, MOS, transistors. Device engineers will go and develop models around that, and they will try to tweak the process to basically get a good device characteristics. Based on that, on the top of it, circuit engineers will come, they would design usable circuits. Then digital design will come, they will actually design circuits using codes and then synthesize them, convert them, and then have a lot of logic around it. And on the top of it will become a hardware solution, software stack, and cloud. That's how it is basically going down. And it's like a kind of a cycle where whatever you make, it becomes, it improves your equipment, then this improves here, everything keeps on. It's like of a positive spiral in the industry. One thing improves another, and all the components of the cycle, they just go above with time. Okay. If we look at our chip, which is an SoC, so it is broadly three components. This is the IO part, input output, the way it talks to the external world. IO is basically responsible for talking to companion chips or through the connectors that I have shown on the PCB to the external chips. You may be just trying to talk to your PC or somewhere, right? Through your card. Inside the chip, portion is analog, which is the custom design using transistors, and then digital. Digital is something what we call is that you write a code and then you convert it into a pre-designed gates, logic gates, that becomes a digital. So major of the work of the digital is done in the RTL coding. Okay. So it will have a synthesized RTL which comprise standard cell library, which will have logic gates, flip-flops, memory blocks. These are like circuit blocks, but they are encapsulated together in a flow such that through formal conversion, you are able to implement your statements into these logic elements and able to check the quality metric on that. Analog section is something very full custom design where you use transistors, resistors, capacitors, MOSFETs, and then to design your blocks. And these blocks implement some kind of system functionality. It could be data conversion, PLLs, transmitter, receiver, oscillator. We will talk about them. So this is a very broad level of overview of the system here. Okay. So coming to, since we had like digital and analog, so what are the advantages and characteristics of digital? So digital is something which has got binary, is the most popular implementation of digital, which is like 1 and 0 implementation. You are electronic engineer, so you know probably all this. Okay, it's a sequence of 1 and zeros, and it can support multiple input output standards. Advantage is that you can easily implement hugely complex designs. You want to have a 32-bit processor or 64-bit processor or some kind of controllers, you can just think at a higher level implement. Basically, it is very automation friendly and extensive use of EDA tools is there. Noise margins are good because signal is switching from very zero to power supply. So the difference is whether signal is close to zero or near to power supply. So that way the chances of corrupting a signal or bit getting inverted are very low. Then you can do like DFT and verification. So DFT is designed for test. You can have formal methods to check the functionality that my elements themselves are working properly as conceived. So what really happens in that case is basically when your chip has come out, you just do a toggle kind of tag, whether it is alive or not. Every path is toggling or not. If everything is toggling, so they are not stuck at it somewhere. So that is the purpose of DFT, design for testability. And most of it is technology agnostic and portable. You can have a processor code in one technology, let us say 16 nanometer, you can take to 5 or 2 or 1, whatever nanometer node is there. And then it is also driven by the push for Moore's law. So Moore's law is basically your transistor capacity doubles in every x amount of time. So this has helped us to basically pack more information in the same millimeter square of area. Okay. Now Moore's law has come under some challenge. It has slowed down, but still it is there. In terms of limitation is that it will always implement Boolean systems which are computable and which have very discrete data, right? It does not support continuous time signals per se fundamentally, but with the approximation we are able to get that, and that is the function of data conversion. Okay. In terms of analog system, this is the first thing that electrical engineers learn: transistors, resistors, capacitors, or inductors to realize a particular function. Okay. And voltage and current, if you look at the diagram here, they are continuously varying like this. If you look at the previous slide, so digital is 1010 is like that. It would be pulse kind of thing. Here basically the signal might be a sine wave or maybe a sine wave changing in amplitude and things like that. So it has to work at those minute things. Okay. Output will also be a continuous function of time. Generally, they support custom input output to a system. Feedback is a norm basically in the analog design. You have to do use some kind of feedback. And need for the analog design is basically digital design cannot realize all electronic functions. Everything cannot be done in digital. So you need an analog around it to get some data from the real world, as we talked in the first slide, and then do some of the computations and calculations in analog. Signal conditioning, you cannot improve in change a signal level of a signal in digital will just give 1 or 0. You can scale the value by having more bits or something like that in a multiplier, but in the real world 0 to 1 would be again 1 volt. But if you want to transfer it to 3 volts or 5 volts or 1.8 volts, the conversion has to be done by analog. Okay, digital cannot do that conversion. Then in terms of design space, so as you go around designing a particular class of circuits, you tend to come to know about the figure of merit of that, like how my area of the circuit is looking like. We know we are in an age of miniaturization where everything which is smaller is more useful. The more compact your gadget, the better it is. And then it has to be a very low power.
So you're talking on mute, sir.
Hello, Dr. Parul. You are on mute, sir.
One pointed out.
Yeah.
Sorry about that. Sorry, guys. So let me just start again fast. So hope you have seen the this, so I'll just move fast. Okay. Hello, am I audible?
Yes.
Okay. Coming to first slide, it's a set of agenda you have already seen probably. We talk about importance and then division of analog and digital, characteristics and differences. What is the body of knowledge? Typical blocks we use in our design, future trends and trends in analog design. We'll just share
Uh,
some NXP examples and questions and answers. Yes, please.
yeah,
Sir,
actually you did not. We just
I-
lost a few seconds of audio of yours. It was not
Okay,
like
maybe in
whole
the
slide.
last
yeah,
second it
from mid
became
session
okay.
Correct,
you
correct,
can
correct.
start.
Yeah,
So okay, that's fine. So probably here you might have lost me.
Yeah,
yeah,
yeah.
correct.
Okay, sorry. I don't know why. Okay, okay. Maybe I'll keep my hand safe. So in terms of analog systems, it is composed of like transistors, resistors, capacitors, like the stuff that electrical engineers do from the starting, and that goes into the professional world as an analog system. So in terms of, I was saying, in terms of design space where we need to navigate area, we want a low area design, and it has to have very low power. It has to work under a very noisy environment. You could have a lot of interference coming from like side gadgets, and you have got a lot of gadgets in your houses and industry and factories and vehicles everywhere. And then there is a performance trade-off. I want to improve the speed, then power supply will actually, my current consumption will go high, or my noise will go poor or something like that. Okay. And process on which we make the design, it behaves differently than the basically the models we are given. So the underlying device characteristics might be different from what we are designing with, so we need to take some margins and make some guesses around that. Okay. And in terms of like key to future is the circuit architecture research. So the architecture that is working now may not serve us 10 years down the line, and we need to be constantly evolving our architecture and solution partitioning to make it work. And one of the good examples of this is that in the earlier days of engineering, most of the things used to be in the analog domain, and digital used to be very small part of the solution. But as we learned around the Moore's law, this became bigger and bigger and bigger with some advantages, and analog has to adjust according to what was being done better in the digital design then could be done possibly in analog design. At the end of the day, consumer consumer is the king, and we want to have the best possible system for the consumer. Okay. Now coming to limitation, basically reuse of analog design is basically across technologies minimal. You can take the concept, but you have to redesign everything and check each and everything upfront. And with like processor codes and all that, the amount of that checking you need to do with the change in technology is much less effort as compared to what we do here. That is also some level of dependence and checks, but this has complete rework, you will say, basically for analog. So in terms of body of knowledge, so a designer needs to be aware of like basic network theory and circuit theory. In terms of like books like von Bolkenberg or network analysis, so you are aware of like what those systems are at a higher level, linear time response, unit step response, and all that stuff. And then circuit theory, circuit simulation, circuit layout, it comes more close to um, VLSI design, where you typically look at MOS transistors or CMOS transistors, some of their theories, inverters, level shifters, latches, amplifier, their simulation, and to be able to do layout. That is a kind of basic work for the analog designer. And in terms of concepts like time and frequency domain concepts, both of them are there, and the designer need to be conversant with both of them, because lot of analysis that gets done in frequency domain, although time domain is much more convenient for us to visualize as people because we live across time. But lots of things like if some signal is getting injected into my waveform and I don't know where it is coming, it might be a collection of various frequencies injected into my system, and if I look at the FFT plot and all that, I can see what frequencies are coming, whether it's coming from power supply or it is coming at some other frequency, and there is a noise source at that frequency, so we can debug it and only then we can fix it. Okay. Device physics and semiconductor manufacturing, you need a good amount of overview. You need to know what technology you are using. Then there are different circuit classes have also come, like RC circuits are there, switched capacitors are there, filters, band gap. These are all different circuit categories, and you can choose to basically specialize around in the beginning, specialize around basically these basically to some level, so that there is some level of comfort around that. In terms of industry roadmap, ITRS, International Technology Roadmap for Semiconductors, they give a projection of how the entire, all the verticals, right from manufacturing to design to testing to software and everything, how semiconductor industry is going to look across a couple of years down the line. Okay. So their roadmaps give a good amount of collection of basically where the civilization is and where it is intended to go in terms of manufacturing and implementations. Okay. Then there are standards in the industry, and these standards they ensure interoperability among the gadgets and they allow different vendors to implement their systems. Okay. So like USB, Ethernet, your SD card, SATA for hard disk, Wi-Fi for connectivity. Then there are audio standards and video standards. So all these standards are there. So they define the system in a very specific manner. All the operations are defined in a way that if two parties they read the specification, build their system, they are going to work. So USB, if your pen drive should work with any laptop you are using. Okay, it cannot be that laptop is from manufacturer A and USB is from manufacturer. They are both supposed to work. That is how standards are written. Okay. Then designers need to have like flair for reading research journals. There's a lot of circuit related work published in IEEE JSSC journals, and you build your background from books and then you see the like what are the different nuances or latest circuits coming, that they will be coming in the journal itself, because book will not update every year. They update in 2-3 decades most of the times, and journals they give you the state of the art performance metric for the circuits and what are the most popular let us say architectures for a particular category. And one good way to go is about read survey papers. So there is a, let us say ADC survey paper or a PLL survey paper. They will actually survey all the research and you will know which kind of solution is working in which application and what performance and price it is giving. Okay.
Hey, you got mute again, actually.
Okay, got it now. So thank you. So in terms of, we are very, there is some issue with this. Okay. We are very cognizant of where we are and where we can go. So people started analyzing like some, let me just, I hope. So it is sensitive to something. Okay. So industrial revolutions, where around 10 years back, someone used the term industry 4.0. And there the things that were driving the civilization was Internet of Things, and then sensor networks, robotics, big data, machine learning, cloud, and all that. Okay. So this is where we are now, basically, in last 7 or 8 years. Okay. And all these things, body of knowledge, when they come across as a kind of a theme with push and directions and kind of synthesizing the entire state of the creation in a particular manner, it also impacts all the manufacturers who are working in a particular area, all the designers, how you put your design, where you give it, and how it is a part of a bigger system. So all this, we have been through a lot of revolution in last 10 years, and this has been phenomenal. So taking a cognizance of this from industry 4.0, there came industry 5.0 conception also. How do we want the future to be shaped? So industry 5.0 set of specifications are going to be more driver for next 20 years for us. 4.0 will they be there, and 5.0 will be there. So as 4.0 will go to a maturity level, 5.0 is beginning to basically go up and stay there. So here it is more about human centric, sustainable and resilient kind of solution. So which means all the industries and the entire ecosystems, they are going to meet the sustainability, work to meet the sustainability targets of United Nations and tweak their processes, designs, solutions. New opportunities are going to come to us. I'm not going to around this, but the thing is that whatever is connected to clouds with their digital twins, your physical world and virtual worlds, they would actually, they come together actually. And with this, analog design and our industry is going to see a lot of shifts and push for designs in a very different way, or making your designs like work through various kind of solutions. So this is just a high level. It's good to have a kind of overview of this. So just in terms of body of knowledge, so I've just put these some common books that designers like to refer, like Fabrication, S.K. Gandhi. Benji Streetman is good for getting your concepts of device physics straight. CMOS circuit design by Holmberg, Gray and Mayer. these two books are really good for basic circuits, and you will get a good amount of idea about amplifiers and single stage and inverting, particularly CMOS side. Okay. Microelectronics by Milman Grable. It's a big book, but in terms of if you just focus on, it gives a very large amount of variety of circuits related to op amps and all other circuits, rather than above two books. Okay. Boyce Bakerly is a very handy book. It also covers another class of circuits like comparators and then Schmidt triggers, inverters, and all that. Design of analog CMOS by Razavi. Razavi is again, it explains the classical analog circuits, amplifier circuits in a very different kind of language, but it's good. Electronic Circuits and Devices by Milman Helke. It's an old book and it used to work closely with Milman Grable. This also covers a lot of circuit types. So these books, most of them would actually allow you to learn around variety of different circuit types with some kind of treatment from the author. Okay. And then on some of the things you need to have a kind of a good amount of grasp of like amplifier or CMOS inverter on gates and all that. Okay. For digital, Maurice Mano is sufficient for an analog designer, I would say. So let us now go to another section, which is like we will just walk over a different kind of subsystems here. And these are the subsystems which are actually, subsystem is something like various analog blocks are like clubbed together or they implement a certain kind of functionality. So timing functionality, the circuits are like oscillators. They are crystal based or RC based, PLLs, clock monitors, frequency multipliers, DFS, discrete frequency synthesizers. So these are the 5-6 types of circuits which I have put here. The point is to basically give you a kind of nudge where you can actually look at in the literature what these circuits are, how they work, and what are the popular implementation. Some of these could be like good, like basically candidate for your own projects and all that. For power managements in the SOCs, typically we will have like regulators to give clean powers to our blocks. Switching regulator typically is outside our SOCs and it is on the system level most of the times because it typically serves a large amount of current. But on-chip linear regulators are popular. Then power on reset is there as your power supply cycles are up and down, and there is also a separate campus connect talk on power on reset which I did in May, and you can actually look at that. It will give you some idea. Some circuit treatment is there. Okay. Then band gap reference, current reference, these are like basic electrical quantities typically circuits needs for themselves or for companion circuits. So we design them. In terms of analog to digital conversion, like there are various topologies, SAR, flash, pipeline, sigma, delta. So we also work on data conversion because of sensors and all those, and they are a staple part of our design. And digital to analog converters like R2R or current mode and all that. No chip is basically complete without some kind of connectivity. In terms of USB, SATA is there for LVDS, HDMI, MIPI display port, like last 3-4 are for mostly for videos, USB for general connectivity, and you also have a like IO for SIM cards, SD cards, which I have not written. And if your chip has an audio interface, it will have some kind of connection for audio. As Manishji told, like we have like wireless work in Pune, so we have got Wi-Fi chipsets, 5G and LTE work around that. Okay. Analog front end AFE is typically you assemble analog blocks together and give it to SOC team. Okay, this is all analog top and it's called AFE. So it will have like drivers, receivers, or like kind of power management circuits all clubbed together or clocking circuits together so that analog integration happens smoothly in the SOC. So typically clocking circuits. Okay. In terms of clocking circuits, the purpose of clocking circuit, what is a clock ultimately? So any system which is working, it has to have a certain sense of time. That is why we need a clock. The purpose of clock is to time your day, time your activities and efforts. So that gets built into electronic systems through clocking circuits. And primarily, basically, digital systems will require clock for its operation because they need to finish certain tasks in a certain amount of time. And different subsystems in a SoC will work at different frequencies because applications are very different. We use a word system on chip for SoC, but it has got very different applications coming together due to convergence of technologies, and their clock requirements are very different. So clocking becomes a very complex part of our design activity, and analog design has to work a lot around meeting all the requirements for different stakeholders. So clocking requirement is basically we will have a one circuit which would be like basic clock source, and we will have a derived frequencies from them. Okay, this is like 40 megahertz is the oscillator, and it is the PLL, another one. So here in a crystal based oscillator, it is the crystal which defines the frequency of oscillation, and crystal is typically, it's a mechanical construction. They have got planes, and their planes are cut in a precise manner. It needs an amplifier inside the chip to support the operation. So we put the amplifier between crystal and EXTEL and XTEL pins. The crystal itself is not a part of semiconductor IC design, but it works closely. And the design has to be very closely coupled to the crystal for good performance. So we put a crystal oscillator amplifier here in the design inside the chip, use a crystal to generate time. The advantage of crystal oscillator is it generates a very accurate clock to the level of you can choose 25 ppm, 10 ppm, 5 ppm parts per million. Actually, the resolution of the frequency is so accurate. So once you get that kind of control over time, you can design your chip actually easily. And so whatever you call as 30 kilohertz or 100 megahertz, it would be 100 megahertz for the lifetime. That is the intention. So the way crystal works at a higher level, if you look at, there is an amplifier and there is a feedback path, and we just compare both of them to give a clock output. So as long as this amplifier design follows certain recommendations for crystal design principles in terms of drive level or impedance it presents or gain, okay, it works as a crystal. Once it works as a crystal, it gives you a clock. And typically the clock is, as I said, it could be mostly from like few megahertz to up to 40 megahertz is the more common number in the industry, and this is mostly determined by what crystal we decide to choose in our application, which one fits around that frequency. We have to design an internal amplifier to support the design. Okay, apart from crystal, which is very accurate, but since it is off chip and external, it might take more time to start up, and there may be some damage to crystal, and you still want to, chip cannot hang. So we have got internal RC oscillators as well. So these are like blocks which will have RC circuits inside, and these RC circuits will generate their sinusoidal oscillation, and with this oscillation you can continue to work. You will not get accurate clock like crystal. It will be plus minus 5% after trimming, or it could vary by plus minus 20 or 30% even. They consume less power, they start very fast, they give you some kind of inaccurate clock in case of emergency or some other tasks. So this is a conceptual diagram. Again, you have got just RC kind of circuits where basically you use RC circuit to with an amplifier in the feedback to generate it. So this RC product will vary with technology plus minus 20-30%, but we will get some kind of clock in case the crystal is not working or some other internal operation is required. Okay, they are low hanging fruit designs. Okay. Main thing comes when you design a crystal, it cannot be designed for gigahertz. It will go up to 40 megahertz, right, let's say. But your clocks might be 5 gigahertz, 8 gigahertz, 10 gigahertz, 2 gigahertz. So the block that works is the frequency multiplier, that is called PLL, phase lock loop. So by using well-known principles of phase lock, you can just scale up the frequency like this. You have got reference clock. After certain number of clocks, you will get another edge. Okay. And once it is locked, it will continue to give out the same frequency again. Okay. So this is again the basic model of a PLL where you have got pre-divider and post-divider. There is the phase detector and loop filter here, and there is a VCO here. So this is something, it works. Actual circuits are very different and bigger, but this is a conceptual diagram which typically gets modeled in MATLAB or some extracted parameters of design. Okay. So for stability and lock time and all that. Okay. So this allows us to give a clock. Now the clock will actually go for data transmission also as much as it will go for some kind of, let's say, processor, making the processor work or tick. Okay. So we have got like a lot of high speed interfaces. These interfaces are basically, let's say, talking to other chips, transferring data at a higher frequency, and you just cannot transfer data like this. So you have to have a lot of special techniques used to be able to drive the pin capacitance of the board or the cable you are using. And the protocols, people have put protocols around that, and these protocols basically they are very common in the industry. You might be hearing a lot, item number 6 here, chiplet, a lot of it, where two chips are within same package and they have got a high bandwidth communication going between two chips. Your s- basically like on your video transmission you have got HDMI display ports and you want a higher resolution, higher frequency. It comes to high frequency basically design basically. Similarly for storage also you want like fast data transfer, USB 3.0, okay, or maybe Thunderbolt or USB Type C. So they are pushing up the data to the higher sides, okay. On the motherboard side you have got PCI Express where you all the peripherals typically talk on the PCI Express interface to the other chips. Okay, so this is just the example of a protocol signaling where we can say basically what is a high speed interface in terms of LVDS. So the design technique here is there is a constant current source here. This constant current source would actually give a current and it leverages the transmission line properties here. So it will go to transmission line, the current will come in one direction from here, it will drop across a resistor, it will come back and it will get sink here. So this way current comes from here, for 1 bit it goes there, okay, on D plus. On D minus basically current will come from this line, it will go here, it will return via this path. So that way this is a differential signaling. You create a differential signaling. So it is around 100 ohms and let's say if you have got a 10 milliamp current, so you will get around 1 volt of swing here basically, and plus minus 1 volt of swing in differential swing. So this low voltage signaling, it allows us to basically match the transmission line characteristics, do more data transfer at a lower power. That is the main bandwidth. So the block that does at a higher level is called a serializer, deserializer. So serializer will have a transmit chip. Transmit chip will have a protocol engine. It will do all the data protocol, handshake, headers, and all that you probably studied in your communication theory. It will encode the data according to the protocol. It will serialize. So everything is parallel here. 10 bits, 20 bits, 40 bits here parallel. It will serial. It will go to a high frequency clock using PLL. It will make the data actually parallel to serial conversion running at 10x or 20x or 40x faster rate. It will go to a driver will drive, okay. Then driver drives a channel would be a ribbon cable or a USB cable or a PCB and a PCB track included. Then channel will go to a receiver chip here it will try to equalize means it will try to cancel that low pass filter transfer function of this line. Once it is able to learn those behaviors, after that it in CDR is clock data recovery, where what typically gets done is basically you try to see the edges in the data. This will restore the signal levels of the signal what is coming at driver. So the purpose of equalizer is to restore the signal levels. When your signal levels are restored, then you try to see where 0 to 1 transition is happening, and then you try to find a clock edge which will match that, and then you will get your data. This data will again go to protocol engine. It will continue to check things if there are some issues. So there would be another transmitter here which will send back the message in terms of protocol handshake. This is a typical SerDes breakdown. It's a pretty complex, and they work up to 20 Gbps or 10 Gbps or 5 Gbps like this, okay. Now coming to data conversion, we were talking about like IoT, medical, sensors and everything. So a lot of this work is getting done by data conversion, where you will use ADCs to sense information, then you will transmit the information. So based on your need, so there is a all these designs in these spaces, they are optimized very differently. Different kind of solutions are there, and different kind of energy needs are also there, okay. So the way data conversion system works, it's like again like a SerDes kind of thing. You have like instead of receiver you have got ADC, instead of transmitter you have got a DAC, and you have got a digital signal processing here. So this DSP system will actually work with this and it will try to work with the real world. Okay. So ADCs again are basically like categorized into what bandwidth they are required, what SNR is required. So low frequency sensors will come here, battery management and all that. So you don't need to do it at a very high frequency, but you may need a higher precision here basically. Okay. Then after that, basically, if you go to the upper side of the spectrum, you will get wideband radio, ultra wideband, and then you will see wireless designs, you will see 5G designs where you need giga samples of data conversion so that you can get, but their SNR requirements would be lower. Here it is higher, but it is coming down if you look at the trend. So for data transmission also and core radar, you want more speed, but you can have a lower number of bits. ENOB is lower. That is how the industry is working with what, because probably we cannot design this and this together. So we try to get high frequency working at a lower performance of the data conversion itself. Okay, so these are some examples from NXP, like NXPs. These are old examples, like we had this 1.35 gigasamples 10-bit system in NXP. Another published one is like 2.6 gigasamples. Another one is basically 3.6 gigasamples. So these are like standalone kind of designs, and you have got a like DC bias state, like quadrature ADC. Okay, sample and track and hold and all that. Okay, calibration is there. So these are all published. You can look at those publications and maybe more to look at data conversion circuits. Okay. In terms of when you go into the lab, the ADC response looks like this. You just give it a sine wave and see where the frequency injection is coming. So there is a lot of places where injections come below your carrier, and it could be because of various reasons in the design. There could be non-linearities in the design. There could be injection from somewhere else that comes here, and there are some harmonics that comes due to non-linearity in the system. Okay. So this is how the spectrum of a ADC looks like. Okay. And you need to do, of course, like offset and gain calibration and everything, because the parts they work from transistor to transistor, so they are programmable and calibration stages are there. Otherwise, they are not very usable without calibration. Okay. Now coming to, let us say, Internet of Things, where basically Internet of Things is where you put uh, sensors and gadgets. It could be in the soil, in your trees, or it could be your drain pipe, wherever. And you have to actually, it has to work on a battery, very low power battery, give you a tick of data. So you know the health of the situation where it is. So you have to make it very small, very compact, very low power, and it puts a lot of challenges for the designers. If you have got earthquake sensor, it would be in a very remote location, and it might be sensing some kind of vibrations and all that. Okay. So what really happens is that basically, so sometimes when you have got actual data coming, your peak power may be very high, but average power would be very low, quiet most of the times, and a lot of things. So people try to basically optimize the solutions around these. Okay. If you look at this one, so this becomes a power management area. Okay. So there are various battery types which are coming here. Is the storage element. You have to basically you are trying to marry your storage element, which will give you power through power management techniques on the load side. On load sides, you have got analog, digital, and transceiver systems, and you try to have a step up or step down conversion based on where it is. If your battery is low voltage and output is high voltage, you will have a step up converter. If your battery is high voltage, requirement is on the low side, you will have a step down conversion. Okay, those kind of things. Okay. So in terms of architectural choices, there are some inductive choices, there are some switched capacitor approaches, and there are continuous time approaches for this power management. So here you can have a variable resistor is the energy transfer element. Here it's a combination of capacitors. You switch capacitor from one to another to transfer the power. Okay. And then here you are switching the inductor. So LDO typically is basically step down function. These two are step out down, and they have got different efficiency ratios. This has the worst efficiency, and here you get a better efficiency, but inductor itself is bigger. And in a practical chip, you might end up with this guy basically, which has a medium efficiency. Okay. So we had talked about voltage regulator. So this is again diagram of this. This is a gain amplifier here. This is output load. There is a variable resistor here. It basically matches the resistance to give a constant voltage here of the system. So you can be very familiar with an operational amplifier where you have got a pass transistor and a feedback path, and this feedback path comes here. So you give a reference voltage here, known reference, and you want a known output voltage here. But the catch here is that it has to support a variety of load currents. So as the transient current happens, spikes happens, it has to continue to support with minimum amount of ripple. That is the LDO design challenge here. Okay, in any LDO, that is the very basic purpose of LDO. So it will have like all kind of things, transient effects, and then you have got your pole zero cancellation here, the feedback network analysis, everything will come here actually. Then it should have a very good power supply rejection also here. So these are the kind of things that go in LDO design. So typically you will have a voltage reference, it could be band gap. Error amplifier is the middle one, the op-amp one, and it drives a pass element. And this pass element basically, it will basically try to the purpose of pass element is to give as much current without loading the amplifier. So this itself can become a big component based on how much power it is supposed to deliver. Okay. And feedback network is typically basically to adjust the voltage. You want to have some kind of programmability here also, like you want to step up the voltage or step down the voltage somewhere. Okay. So the actual system would be slightly bigger than this. Coming to this is like typically snapshot of a layout where you put the transistors. You try to ensure that it follows some kind of pattern, common centroid and matching, and then you have got guard rings around that, and you embed the analog solution like this. Okay, this is how one of the samples of the layout that is done in the design. Okay, so this is all about my presentation. I have done through my talk. Okay, I hope I have not taken much time. So this is you. It's a Q&A time for you.